Asteroid 2024. Year 4 caused quite a stir last year when it was discovered, and originally calculated to have a 3% chance of hitting Earth. Since then, models have been refined, and while it no longer has a chance of hitting Earth, it does have a 4% chance of hitting the Moon in December 2032. As that time gets closer, we'll have a better idea of the probability. But engineers and scientists are also planning for what we would need to do to ensure it doesn't hit our only natural satellite at all. A new paper from NASA and a bunch of other researchers details potential missions and timelines that could make sure the Moon isn't pummeled with a decent-sized asteroid in less than a decade. There are no definitive plans to have a permanent human presence on the Moon by that point, so it wouldn't directly affect any human activities. Except an asteroid this large could create a huge debris field that would increase the micrometeoroids hitting the Earth by up to 1,000 times the normal background average for a few days. While that would make for one of the best meteor shows of the last few hundred years, it would also pose a danger to Earth-orbiting satellites and even astronauts on the ISS and other space stations, assuming they're still there in 2032. Really? There are only two options to stop that eventuality if 2024 Year 4 is indeed going to hit the Moon, which, to be honest, is still very unlikely. One option is to deflect it. The other is to destroy it. Deflection would be preferred. Simply moving its orbital path slightly would ensure it would miss both the Earth and the Moon. The earlier we could do it, the smaller nudge would be needed, so it's better to do it sooner rather than later. However, in order to accurately deflect 2024 Year 4, we need to know how much it weighs. We have a relatively good estimate of its diameter, around 60 meters, give or take 10%. But estimates of its mass depend on its density, which is hard to calculate from so far away. The asteroid's weight could range from 51 million kilograms to over 711 million kilograms. And the amount of energy needed to move either of those weights, a very precise amount, is massively different. If a mission to deflect it is based on the wrong mass calculation, it could potentially accidentally change its trajectory to make the problem even worse, including potentially redirecting it towards Earth. Engineers could design a reconnaissance mission to try to get a better estimate of 2024 Year 4's mass, but the best time to do so would be in 2028. Only 3 years away. Designing and launching a purpose-built mission in that tight time frame has never been done before. And while it could be for a mission to solve something that's a high enough threat level, 2024 probably isn't it. That being said, we could repurpose existing missions that are already in space or in development. OSIRIS-APEX, the name for the extended mission for the OSIRIS-REx mission, that is currently on its way to Apophis, another near-Earth asteroid. Psyche could also be commandeered on its way to its main belt target. But in either case, those missions would have to give up their intended targets to get close enough to 2024 Year 4. Another option is Janus, which is currently sitting in storage, but it's unclear how well they would do in defining its weight. Given the uncertainties around the deflection option, the paper notes that the other option is at least feasible. Destruction of an asteroid can come in one of two forms. The first is kinetic, basically hitting it with something big and heavy enough to break it into smaller 10-meter chunks. DART recently proved the idea of redirecting an asteroid by doing the same thing. Hitting it with the intention to destroy it would be a different level of difficulty, though certainly one that we could design and build in time for a launch window of sometime between April 2030 and April 2032. Other option to destroy it will stir a feeling in the hearts of 90s kids: we could nuke it. It might not involve Bruce Willis sacrificing himself, but setting off a nuclear explosion at some height off the surface of 2024 Year 4. Known as the height of burst, we would still need some reconnaissance to try to tailor the explosion. But the paper calculates that a 1 megaton nuke would be enough to disrupt 2024 Year 4, no matter what size it is, and that is well within our current nuclear arsenal. To be fair, We've never tested a nuclear explosion in space with the intention to deflect an asteroid before, but physics certainly says it's possible. And we have simply tested a nuke in space, though it was back in the 1960s, most notably with Starfish Prime, which was launched in July 1962. It's as much a political decision as a technical one as to whether that would be a viable option for this particular threat to our planetary system. We're not even sure if 2024 YR4 is actually going to hit the moon yet, and we won't find out until 2028. But if we find out it is, it's best to at least have the ability to disrupt it if we want. That decision will have to be made in the next few years, as the window to get missions off the ground is growing smaller every day, whether they're nuclear or not. The next frontier for precious minerals could be much closer to home than the asteroid belt out past the orbit of Mars. A new paper proposes that the minerals borne by these asteroids may have come to us and are now scattered across thousands of impact craters on the moon. There, up to 6,500 impact craters may contain precious platinum group metals such as platinum, palladium, and rhodium. Furthermore, some 3,400 impact craters may contain water in the form of hydrated minerals, a crucial molecule for any human exploration of our only long-term natural satellite. These values are 1 to 2 orders of magnitude larger, been larger than the number of ore-bearing near-Earth asteroids estimated by Elvis 2014, writes a team led by independent astronomer Jayanth Chenamangalam, implying that it may be more advantageous, and hence more profitable, to mine asteroids that have impacted the moon rather than the ones that are in orbit. There are numerous potential benefits to mining in space. Earth's resources are finite. For one, there's only so much accessible metal in our planet's crust. Mining is also often quite destructive, damaging land and habitats, and generating tremendous amounts of pollution. In addition, mining in space has benefits for space exploration. Having access to water on the moon, for example, would help mitigate the challenges of either transporting water from Earth or recycling it in situ. Many asteroids are believed to be rich in precious metals, specifically the platinum group metals, which possess properties that make them highly prized for industrial and medical applications, but are rare. But asteroid mining presents its own challenges, even aside from the astronomical cost. Near-Earth asteroids are pretty scarce. They're also very complicated to reach and tumble in space in ways that make them difficult to navigate. The moon, by contrast, just hangs out in Earth orbit at a predictable distance, with the same side facing us always. That doesn't mean the moon is easy, but it's a darn sight easier than an asteroid. The big question that presents itself is then, does the moon have the platinum group metals and water that we need? Chenamangalam and his colleague embarked on a survey of asteroid impact craters to find out. Certain metallic-type asteroids are thought to be rich in metals, including the platinum group. Meanwhile, carbonaceous asteroids are thought to be rich in hydrated minerals. When an asteroid smacks into the moon, some of it vaporizes, but recent evidence suggests that significant portions of the asteroid body can survive under certain conditions. For particularly large, complex craters, the debris is swept into the center of the crater, where it forms a central peak. By counting the large craters that could be the result of an impact by these asteroids, the researchers estimate that there could be quite a lot of valuable metal lurking on the moon, even factoring in that much of an asteroid may not survive an impact, especially for hydrated bodies that lose water to heat. The statistical estimates still ran into the thousands of craters. Up to 6,500 craters larger than 1 kilometer across could contain platinum group metals, although the ore might be finely dispersed through the lunar regolith and difficult to access. If the search is narrowed down to craters larger than 19 kilometers across with a well-defined central peak where the ore is likely concentrated, the number drops to 38. Meanwhile, up to 3,350 craters larger than 1 kilometer could have water, narrowed down to 20 larger than 19 kilometers with concentrated deposits. This means the Moon represents a statistically richer hunting ground for platinum group metals than near-Earth asteroids. It may still be that asteroid mining is in humanity's future. However, the Moon appears to represent a more achievable and practical stepping stone towards that goal. The next step is figuring out exactly which craters hide the treasure and how to mine them. The researchers suggest that remote sensing from lunar orbit, rather than costly and not guaranteed to succeed landers, is the best option for identifying which targets are most worth pursuing. For 24 hours a day, 7 days a week since November 2000, NASA and its international partners have sustained a continuous human presence in low Earth orbit, including at least one American streak that will soon reach 25 years. When viewed in the history of spaceflight, the International Space Station is perhaps one of humanity's most amazing accomplishments, a shining example of cooperation in space among the United States, Europe, Canada, Japan, and Russia. But all good things must come to an end. In 2030, the International Space Station will be deorbited, driven into a remote area of the Pacific Ocean. I'm an aerospace engineer who has helped build a range of hardware and experiments for the ISS as a member of the spaceflight community for over 30 years and a 17-year member of the NASA community. It will be hard for me to see the ISS come to an end. Since the first pieces of the International Space Station were launched in 1998, the station has been home to significant research accomplishments across domains that include materials science, biotechnology, astronomy and astrophysics, earth science, combustion, and more. Astronauts performing research inside the space station and payload experiments attached to the station's exterior have generated many publications in peer-reviewed science journals. Some of them have advanced our understanding of thunderstorms, led to improvements in the crystallization processes of key cancer-fighting drugs, detailed how to grow artificial retinas in space, explored the processing of ultrapure optical fibers, and explained how to sequence DNA in orbit. In total, more than 4,000 experiments have been conducted aboard the ISS, resulting in more than 4,400 research publications dedicated to advancing and improving life on Earth and helping forge a path for future space exploration activities. The ISS has proven the value of conducting research in the unique environment of spaceflight, which has very low gravity, a vacuum, extreme temperature cycles, and radiation, to advance scientists' understanding of a wide range of important physical, chemical, and biological processes. But in the wake of the station's retirement, NASA and its international partners are not abandoning their outpost in low Earth orbit. Instead, they are looking for alternatives to continue to take advantage of low Earth orbit's promise as a unique research laboratory and to extend the continuous 25-year human presence some 250 miles above the Earth's surface. In December 2021, NASA announced 3 awards to help develop privately owned, commercially operated space stations in low Earth orbit. For years, NASA has successfully sent supplies to the International Space Station using commercial partners, and the agency recently began similar business arrangements with SpaceX and Boeing for transporting crew aboard the Dragon and Starliner spacecraft, respectively. Based on the success of these programs, NASA invested more than $400 million to stimulate the development of commercial space stations and hopefully launch and activate them before the ISS is decommissioned. In September 2025, NASA issued a draft announcement for Phase 2 partnership proposals for commercial space stations. Companies that are selected will receive funding to support critical design reviews and demonstrate stations with 4 people in orbit for at least 30 days. NASA will then move forward with formal design acceptance and certification to ensure that these stations meet NASA's stringent safety requirements. The outcome will allow NASA to purchase missions and other services aboard these stations on a commercial basis, similar to how NASA gets cargo and crew to the ISS today. Which of these teams will be successful and on what timescale remains to be seen. While these stations are being built, Chinese astronauts will continue to live and work aboard their Tiangong space station, a three-person, permanently crewed facility orbiting approximately 250 miles above the Earth's surface. Consequently, if the ISS's occupied streak comes to an end, China and Tiangong will take over as the longest continually inhabited space station in operation. It's been occupied for approximately 4 years and counting. It will be several years before any of these new commercial space stations circle the Earth at around 17,500 miles per hour, and several years before the ISS is deorbited in 2030. So, while you have a chance, take a look up and enjoy the view. On most nights when the ISS flies over, it is simply magnificent. A brilliant blue-white point of light, usually the brightest object in the sky, silently executing a graceful arc across the sky. Our ancestors could hardly have imagined that one day, one of the brightest objects in the night sky would have been conceived by the human mind and built by human hands.